Okay, the poster is in that corner. There's another poster next to it that's also mine, which I'm not supposed to, but I'm going to anyway. So this is about yet another way to carve up the evidence lower bound. It's work with Matt Johnson from Google Brain. The setup is we have an IID latent variable model of the type that we all know and love. We've got some latent z's, we've got some observed x's, and we're interested in doing variational inference to do maximum marginal approximate variational EM. This work is really about further decomposing this scale divergence term that shows up in this equation, right? So on the left, we've got this average reconstruction quality. On the right, we've got the average scale divergence between the posterior approximation that we wind up with and the prior, if you like, on Z, or the marginal distribution of Z. So here's the big result. We can further decompose that KL term into two pieces: a mutual information between Z, between the Z vector and the index of the observation that it's attached to. So that's in some sense how informative, if I show you this latent variable, how good a job can you tell me of telling me which observation that's attached to. And then there's this second term, which is the marginal KL divergence between the average approximation to the posterior, averaging over all the observations, and the prior. The interesting things about these terms is that they're bounded. The middle term, the mutual information terms between 0 and log n. The term on the right is 0, and interestingly, we can set it to 0 exactly if we set p equal to that marginal q. We did an experiment, and I won't go into any details about it, but the implication that I'm taking away from it is that P of Z matters. Compare with rethinking LDA, why priors matter, and this decomposition gives us a diagnostic for how much. And if you're interested in hearing more, then come to the poster. Thanks.
Thank you. So next speaker is sorry, no, that's not true. Volodymyr Kuleshov is the next speaker.
So basically, what this work is about is in machine learning, many problems of interest are best described using the language of undirected graphical models, such as an MRF. But these models are often intractable because we have to deal with the partition function Z. And here we propose a technique for dealing with this, for working with such models that involves a variation, a lower bound on the log likelihood of undirected graphical models. So the key part that makes it work is an upper bound on the partition function, a variational upper bound on the partition function. Typically, if you do the standard elbow, this gives you a lower bound, which is not suitable for learning. So the key idea behind this, or the key observation, is that, so first, if we consider an important sampled estimate of the partition function Z, where Q is the proposal distribution. If we look at the variance of this estimate, then the variance represents an upper bound on Z squared. And we can use this as our upper bound. Now, it has several nice properties. For example, when Q equals P, this is tight. When Q is in an exponential family, then this is convex in the natural parameters of the exponential family, for example. This works when Q is similar to P. If you imagine P being a very peak distribution and Q is uniform, then this would not work. But our goal here is learning, and so what we can do is we can start with we initialize both P and Q, where they are both relatively uniform, and then as we learn P, we also optimize Q using gradient descent, so that Q gradually tracks P, and this variance is under control during the entire learning process. Now, of course, for all of this to work, we need Q to be in a flexible family of distributions, and what we propose here is a class of distributions which themselves involve latent variables, auxiliary variables, and there's a relaxation of our earlier bound, which we can optimize by various, if we instantiate Q in different ways, we get back something which looks very similar to several existing methods that have been proposed. And in particular, we can use neural nets to parameterize many of these distributions. In our experiments, what we in general observe is that this is competitive in terms of speed with existing methods, but we can track we have an estimate of the log likelihood, which is close to something that we would get using, for example, yield importance sampling, but this is less expensive. So for more details, come see the poster. It's the last one on my right. Thank you.
Thank you. Dan Alcazar is next.
Hi, I love variational inference. But every time I optimize the algo, I run into some trouble. For example, the approximate posterior Q with parameters lambda can be under-dispersed or sensitive to initialization. How can we think about starting to fix some of these issues with variational inference? First, we can recognize that you can recover gradient descent by solving this update equation. The first line is the first-order Taylor expansion of the objective. On the second line, you have a proximity operator in Euclidean space. If you solve this update equation, you recover standard gradient descent. But what does this mean for the variational parameters lambda? It's not ideal. Think of a Gaussian. The Euclidean constraint is just a ball for a given mean and variance. But think of a Gaussian. The variance affects where the Gaussian places probability mass much more than the mean does. So for variational inference, you want to think about designing different proximity operators that constrain one dimension of the variational parameters, but not the others. So we want to think about how to constrain this ball into more of an ellipse and get better statistical properties of our approximate posterior. How do we do this? We introduce a new proximity operator. We choose k, the magnitude of the constraint, d, a distance function, and f, some function of the variational parameters. This enables us to design constraints relevant to variational inference. For example, in the Gaussian, if we choose f to be the entropy, then we will only squash the variance dimension, because the entropy of the Gaussian is only a function of the variance. And this gives us what we want. We've squashed the Euclidean ball constraint into more of an ellipse. How does this work in practice? Yes. So we show that variational inference, in some cases, does not recover correct solutions, in this case, cluster means on the left. But proximity variational inference with an entropy constraint does recover true solutions in as much time. In a sigmoid belief net model of images, we can reconstruct the data where variational inference cannot. I'd love to get more feedback on this, so please grill me on this. The poster will be over there. Thank you.
Thank you. So next speaker is Qiang Liu on Stein Variational Gradient Descent.
So I'm Qiang Liu from Governors College. So I'm going to talk about Stein Variational Gradient Descent, which is a new framework for doing variational inference using by applying iterative transforms over particles to approximate the target distribution that minimizes the Q divergence. So the idea is that, let's say we initialize some particles using some simple distribution, and then we iteratively update the particles using updates, incremental updates like xi plus epsilon phi, where epsilon is the step size and phi is the perturbation direction. So the perturbation direction is chosen to optimally minimize, so make the decreasing rate of Q divergence maximized, and this can be solved by using this functional optimization. So it's an optimization over the function space. What's interesting is that this optimization actually has a closed form solution. Without going into much detail, this is the algorithm we essentially get that can optimally decrease the Q divergence incrementally. So it has two terms. The particles are driven by the gradient, which force the particles to go to the high probability range, as well as a positive force that enforce the particles to be different. So a nice property of this algorithm is that it actually reduces to gradient descent if you only use one particle. So I should have a video here, but it's missing now. But feel free to check my website. I have a video there. Turns out, again, without going into much detail, there's an extension of this algorithm. In this case, you can actually train a neural network to get a set of particles that directly approximate the distribution by following the Stein variational dynamic. And it works very well, so we actually use it to approximate molecular training of deep energy models and get results competitive with GAN. So feel free to come by. I will actually talk some of these ideas tomorrow in the Bayesian deep learning workshop. So thank you.
Thank you. Okay, our next speaker is Hans Christian Ruiz-Euler.
My name is Hans Ruiz, and we are presenting in this poster a new smoothing method. The smoothing method is called PySmoother, and it's a new adaptive importance sampling method that efficiently samples from the posterior distribution or smoothing distribution over hidden diffusion processes in continuous time, continuous spaces. In general, it is very difficult to sample from this posterior, and usually you resort to importance sampling, for example. And this has a major drawback because if the posterior, or if your proposal distribution is far away from your posterior, then you will get weight degeneracy, meaning that only few waves of the importance sampling will be relevant for your estimation. So that means that the effective sampling size is also very low. So we tackle this weight degeneracy by steering the particles using KL control in order to increase the likelihood of the time series. This steering is equivalent to adapting your proposal distribution. Recent work in our group has shown that the optimal controller is actually the optimal importance sampler. So if you would have the optimal control, then you can just straightforward sample from the posterior distribution. Of course, it's very difficult to get the optimal control. So the good news is that if you have better controllers, you also have better importance samplers. So what we have to do is we have to approximate well enough our controller, and so we learn a parameterized controller. So we need a good parameterization in order to have a good approximation to the optimal control. And we need to be flexible in the design. So we use a deep neural network to learn the controller, or as a controller. We exemplify this with fMRI data, and our aim was to infer the neuronal activity given the fMRI time series of the motor cortex. And on the left, we compare it with the bootstrap filter smoother, and on the right, we show that the sampling efficiently increases several orders of magnitude. Yeah, so for more details, my poster is over there, so thank you very much.
Thank you. So the next speaker is David Moore on symmetrized variational inference.
Cool. Okay, thanks everyone. So I'm interested in models that have symmetries. So that means that your posterior is invariant under some class of transformations, like for example, sign flips or rotations or permutations. This comes up basically if you're learning some form of latent representation. Often that's not quite identifiable. And so you get these sort of highly multimodal posteriors, but that are also very, very structured. Right? And so I think often people sort of assume that you can ignore this. You have sort of this mental picture where these symmetric modes are very well separated, and you minimize KLQP, and so you find one mode and they're all the same, so maybe you're happy. But I think this picture is not always correct. So depending on your data and your model, you can get cases where actually modes are close together and your Q distribution finds some degenerate point that tries to straddle multiple modes instead of actually modeling any individual one. So this can cause potentially a range of problems. So there's actually some theory related to this analyzing Bayesian matrix factorization showing that the VB solution essentially thresholds the singular values. So no matter how much capacity you add to your model, it will only learn up to some fixed rank approximation. And this is called an implicit regularization effect because the true posterior doesn't do this. It comes from approximate inference. And empirically, something similar is maybe going on in VAEs. So my question is, how can we build approximations that let us actually use our full model capacity? And the proposal is that if we know our posterior has a certain set of symmetries, we should explicitly model that in our Q distribution. And a simple way to do that is to start with something like a Gaussian and just construct the mixture distribution over a symmetry group. It turns out when you do that, you just get back the original elbow plus an extra KL term, which is always non-negative, so it's a tighter bound. And you can think of that extra term as encouraging you to find these sort of non-degenerate solutions and really model a single mode correctly. It turns out that in some cases we can do this efficiently. In sort of toy cases, we can actually compare predictions to the true Bayesian posterior and see that we avoid this implicit regularization and get better predictions. For matrix factorization, you can compute a Gaussian mixture with your orthogonal group in some cases and actually efficiently see that we can use the full model capacity, and that also gets us out some better predictions. This is still sort of very preliminary. There's a lot of questions I'm still exploring, so I'd love to discuss it at the poster. Thanks.
Thank you. Okay, now our last talk here is going to be Francisco Ruiz, rejection, sampling, variational inference.
Okay, hi everyone. I'm going to talk about rejection, sampling, variational inference. The first author, Christian, couldn't make the trip to Barcelona, but Scott and myself will be around to explain the poster. So our poster is somewhere on your left. Okay. So we want to do variational inference because we want to approximate some complicated posterior distribution. And we want to apply the parameterization trick because it produces very low variance estimators of the gradient. In practice, one single sample is enough to estimate the gradient. However, parameterization is only available for certain distributions. And what we do here is to extend our parameterization trick to other distributions that are more complicated. So the main idea is that if you think about it, for every random variable that you generate on your computer, you first simulate from some elementary distribution and then apply a set of deterministic transformations. So in theory, you should be able to reparameterize any distribution. However, there is a challenge that we didn't think about, which is that in computers we use projection sampling. This introduces some discontinuities that prevent us from pushing gradient into expectations. So we solved that by marginalizing out all the auxiliary variables, all the auxiliary accept-reject variables that we use in projection sampling. So I won't go into the details, but this allows us to take advantage from many, many years of research in projection sampling and apply these ideas to variational inference. So this is just a plot showing some results. This is the evolution of the elbow, the objective function, and we basically outperform state of the art.
Thank you.